Okie dokie. Let's see. Section 2.4, the second derivative. Okay, so let's continue our analysis of what's called the derivative. Continue discussing the derivative, try to understand it better, try to understand things that we didn't understand about it before, and try to take the next step. Let's get started. So, recall that for a function f of x, we can take its derivative, f prime of x. We do that by taking the slopes at each point. We estimate the slopes at each point. And what we get is another function. We'll have a much smoother process to do that very soon, given like an equation. But for now, just think about it like that. It's another function, it represents the slopes of the function f of x. And we can use the derivative to tell us things about the original function. Like for example, is the function increasing or decreasing at a particular point? And does that function have any maximums or minimums? We can actually tell by the derivative. Alright, so we can do this process again. So we can look at the slopes, essentially the slopes of the slopes, like go the next level, right? So we take the derivative of the derivative, and we call that the second derivative. And we just write that with another prime symbol. And if you're worried about the semester, if we're just going to continue to take the derivative again and again and again and again, and have like the 15th derivative or something like that, don't worry, we're not going to do that. All right, we basically never go past the second derivative. After that, we kind of get diminishing returns in terms of the amount that we learn about the original function f of x. All right, basically we get the idea after we take the second derivative. So this, so all the rest of the sections will not be just taking more derivatives. We'll be taking derivatives, but of different functions, not the same function over and over and over. Okay, anyways, so what does this second derivative tell us? First of all, it tells us something about the concavity of the original function, f of x. So the second derivative tells us if the function is concave up, concave down, if there's any inflection points where it changes concavity and so forth. Right. Directly, it tells us whether the function f prime is increasing or decreasing, or has any local maxes and mins. All right, these all line up on a graph, and so let's get some practice reading what we can learn about the functions from the graphs and their derivatives. All right, so here's a function f of x. This is the function x squared, and its derivative looks like this. You'll just have to take my word for it at this point. It's the function 2x, and so it's a line. It's an increasing line through the origin. And when you take its derivative, you get a horizontal line that is positive, right? And I put them directly above each other because all these things line up. Like this y value tells us me something about the function f at this point. So for example, down here, see how we have negative numbers? We have a negative graph. Well, this represents the slope of this graph. And see how this slope is negative? Okay. And we have positive numbers over here, which means the slope should be positive over here. Okay, not only that, but also notice that even though these numbers are negative, this graph is negative, but also notice how it's getting closer and closer to 0. They're becoming less negative. So, and notice the slope is negative, but it becomes the slope becomes less negative until it just levels off. It just rounds off completely. And the slope becomes positive, and it becomes more and more positive. As the slope gets higher and higher, see how this function gets steeper and steeper. Okay, but notice that, and looking at the connection between these two here, this function is actually, the rate of change is constant. It's a line. Right? It has a positive constant slope. And notice this function should tell us the slope of this function, and it's a positive constant number. Right? So the fact that the second derivative is a positive constant should tell me that the previous function has a positive constant rate of change, which it does. All right, so there's close correspondence between all these things going on. And yeah, so we should keep it in mind. Okay, now just to add to this graphic a little bit, so each one, when you take the derivative, it tells us how the original function is changing. When you take the second derivative, that tells us how the first function is changing, or the first derivative is changing. The second derivative, usually we use that to tell whether the original function is concave up or concave down. So notice how the second derivative is positive constantly, and notice how the original function is concave up everywhere. All right. So the fact that this is positive, this tells us that the function is concave up everywhere. It has a cup shape. Every point on the curve is part of a cup shape. All right. All right. Good. So just as a list of things here, if the second derivative is positive, that means the function is concave up. We just talked about that. And it also means that the function f prime is increasing. And vice versa. If we don't have this situation here, but if the second derivative were negative, that must mean that the original function is concave down, and also that the derivative would be decreasing. All right, let's move on. So just to kind of give you said in a different way slightly, the point of this slide really, even though it's not anything, I mean, it's stuff I've already said, but it's just to emphasize that these qualities of a function of being increasing or decreasing or concave up or concave down, they're point-wise. Right? It depends on the point that you're looking at on the graph. Right? So even though there might be multiple points on the graph where the function is increasing or decreasing, we still have to look at each point. It's something that you definitely know and you definitely have encountered, but I just want to make sure that that's firmly on your radar. Okay, and a function being increasing, that means that the derivative increasing at a point, that means that the derivative at that point is positive. All right. And a lot of times we will just say, instead of saying f prime of a, we will just say f prime. That's pretty common. So we would just say f prime is positive. And a function is decreasing, that means its derivative is negative. We might just say f prime is negative. Function is concave up if its second derivative is positive. That also means that f prime is increasing. F prime is increasing. All right. Second derivative tells us how this function is changing. So if the second derivative is positive, that must mean that the slope of this function is positive, meaning that it's increasing. And a function being concave down, that means that the second derivative is negative, which means that the slope of f prime is negative. In other words, f prime is decreasing. So I would guess that for for many of you, it's hard to make the distinction between all these things, to get all these details straight. And I just like to say it takes time. It takes time. These are kind of subtle observations that we're asking you to make here, and it takes time for your mind to get acclimated to these kind of observations. So, but we will practice and we will try to get it right. All right. So let's see another example here. This is keeping in mind what we just talked about. Here's I guess I could have I didn't need this much space between this stuff, but okay, forgive me for that. So we have the function here, and I just made some observations about it. So let's just go through these one by one. I said that f prime of 3 is negative. It's less than 0, it's negative. F prime of 3, so that means the x-coordinate is 3. So here's where the x-coordinate is 3 on the graph, and the derivative being negative, that should mean that it's decreasing at that point. Is it decreasing at that point? And the answer is yes. It's going down from left to right through that point. All right. Even though the function is 0 at that point, its slope is negative. All right. And f prime of 4 equals 0. That's the next one that I said. F prime of 4 is 0. All right. This is critical to observe. So f prime of 4. So the x value is 4. So we're talking about this point here on the graph. And the slope is 0. If I were to make the slope of the tangent line, it would be a horizontal line. To the left of it, it's decreasing. To the right of it, it's increasing. So these points where we have the slope being 0, that's usually a maximum or a minimum. All right, so this is a way to find relative extrema of functions. All right, f prime of 5 greater than 0, that's the next one I said here. So we go to x equals 5, and we look at the function, and f prime of 5 being positive, that should mean that the function is increasing at that point, and sure enough, it's increasing. It's going up from left to right. All right, now how about the second derivative? I said that f prime of minus 1 is negative. So if I go to minus 1, that's this point on the graph here, and f double prime being negative, that should mean that the function is concave down. And is it concave down? And yeah, it's part of a frown shape. In fact, all these points are part of a frown shape. All right, so definitely this x-coordinate here is. All right. I said that f double prime of 4 is greater than 0. So here's kind of a interesting thing. So even though the derivative is 0 at this point, it's still concave up at this point. At this minimum here, it's the bottom part of a cup. Right, so it's definitely part of a cup shape, and so it's concave up at that point. All right, and I said that f double prime of 2 is about 0. So let's see. That means x is 2, so I'm talking about this point here. All right, what would it mean for it to be 0? That means that it's neither concave up or concave down. And this is where you're going to find your inflection points for the function. So it's the function is part of a frown all the way up until about x equals 2, where it switches. Over here it's concave up, and over here it's concave down, and somewhere in between here, maybe more like 2.5 or something like that. Maybe not exactly 2, but f double prime of 2, f double prime of 2.5 or something like that. That's where you have the second derivative is 0. All right, so functions are 0 on the x-axis. Their derivatives are 0 at maxes or mins, and the second derivative will be 0 at inflection points. All right, so for example, just to give you one more example, the same thing that we were just talking about here. So here's a function. It's basically x cubed. Just translate it up a little bit. And I said that for negative x values, so for the left bit, it's concave down. It's part of a frown. And so the second derivative is negative. And for the right bit, so for positive x values, the second derivative is positive, meaning that it's part of a cup. All right, and that point where it changes, from concave down to concave up, that's where the second derivative is 0. That's an inflection. It's not always an inflection point where the second derivative is 0, but it usually is. All right, point where it changes inflection. If it changes inflection, then the second derivative is definitely 0. There are functions like x to the fourth, which we won't see very often, but where the second derivative is 0, but it's actually not an inflection point. But definitely, if you have an inflection point, that will be where the second derivative is 0. All right, a little bit of a logic thing there. All right. Now, the last thing, it says there's 3 more slides here. Really, just got one more example to go. Here, I just broke it up into 3 slides. And it's really to help you with Wiley Plus homework problem or 2, where you're asked to, instead of looking at a graph to determine things about the derivative or the second derivative, you're asked to look at a table and make some guesses as to what the derivative, what you can say about the derivative or the second derivative. All right, so the first question here says, does the derivative of this function appear to be positive or negative between t equals 1 and t equals 2? All right, so the derivative being positive, that should mean that the function is increasing. So do I have that case here? Yeah, I'm going from 11 to 15. That's going up. So that's increasing. Okay, good. All right. And before I show the next slide, because the answer to the next slide has the answer to the first 2 questions, so I'll go ahead and talk about it first. How about h double prime? How to guess this from looking at the table? So how to guess what if the function is concave up or concave down by looking at the table? Well, remember what I said a long time ago about how being concave up means the slope is increasing, means that it should be increasing by more and more. All right, is that happening here? So let's see, between t equals 1 and t equals 2, do we see a pattern of increasing by more and more, or the opposite? So it looks like we start at 6 and we go to 11, that's an increase of 5. And then we increase by 4, and then we actually start to decrease. So this looks like a concave down situation because the slope is actually going down. All right, so between t equals 1 and t equals 2, it's actually a concave down function. So that's what I put here. For the first question, we said that it was increasing because it's going up. But for the second question, the second derivative should be negative here, because if we look at how the function is changing, we go up 5, and then we go up by 4, and then we go down 4. So the amount by which we're going up starts going down, and then actually we start going down. So that's definitely decreasing slope. All right. How about the third question? Let me go back. How about the third question here? Does h prime appear to be positive or negative between t equals 2 and t equals 3? So we're talking about what the function is doing for this little bit here. So it's going from 15 to 11. That is a decrease, which means that the derivative should be negative. The slope should be negative. So that's that. How about the second derivative between this? All right, between these 2 points. Do we think that's positive or negative? So let's look at not only you have to look at more than just these 2 points. you have to consider surrounding points as well. So if I look at what happens from 15 to 11, that's going down by 4. And then I'm going down by 5. So I'm going down by more and more, it looks like. And so that's a concave down situation. It's concave down. Okay, the slope is decreasing because it's becoming more negative. So that's what I said here. Between 2 and 3, we have a decreasing function, so this derivative is negative. And then the second derivative is also negative because the slope is decreasing by more and more around here. Okay, if you look at all the what's happening to these y values, it might help to make little notes off to the side here, where I put like +4, -4, -5 to spot the pattern and see the trend. So I might put like a +4 off to the side here, a -4 here, and a -5. Maybe I'll make a graphic for that at some point. But anyways, that's how it works, and hope that made sense, or some of it at least. And good luck with your YLoop Plus and anything else that you got going on these days. All right, that'll be all for now. Have a good day.